Rocket science has a reputation for being incredibly complicated. But by the end of this video, you will understand 8 fundamental concepts that every rocket scientist needs to know. Starting with number 1, rocket thrust. Thrust is the force that pushes a rocket forward. It comes from rapidly ejecting high-speed exhaust gases out of the engine nozzle. Inside a rocket engine, propellant is burned to produce extremely hot gases, which expand and are forced out of the nozzle at very high speeds. As these gases rush out of the engine, they carry momentum away from the rocket. Rocket engines are essentially designed to convert stored chemical energy from the fuel into directed motion. Inside the combustion chamber, propellants undergo an extremely energetic chemical reaction, producing high-pressure gases at temperatures of several thousand degrees. Because these gases are under enormous pressure, they naturally try to expand in every direction. But the engine nozzle channels this expanding gas so that it can only escape in one direction, out the back of the rocket. The nozzle itself is shaped to accelerate the exhaust to extremely high speeds. As the gases expand through the nozzle, the high pressure of the combustion chamber ejects the exhaust with high kinetic energy, meaning the exhaust leaves the engine traveling incredibly fast. Some rocket engines eject exhaust at speeds of several kilometers per second. The amount of thrust determines whether a rocket can lift off, accelerate, or maneuver in space. On the launch pad, the rocket must produce more thrust than the force of gravity pulling it downward in order to lift off. But once it's in space, thrust can be used more gently, often in short bursts, to change the spacecraft's speed or direction. For example, launch vehicles typically produce millions of newtons of thrust in order to overcome gravity. In contrast, spacecraft operating in orbit may only fire small thrusters that produce tiny amounts of force. Even a small amount of thrust can gradually change a spacecraft's trajectory when applied over time. Number 2, rocket propellant. Propellant is the fuel a rocket burns to create thrust. Rockets need to carry everything they need to operate, including the chemicals required for combustion. Because there is no oxygen in space, most rocket propellants come in the form of both a fuel and an oxidizer. Rocket propellants usually come in 2 main types: liquid and solid propellants. On Earth, most engines rely on oxygen from the atmosphere to burn fuel. Car engines, jet engines, even steam engines all depend on oxygen in the air. But rockets cannot rely on atmospheric oxygen once they leave the atmosphere. This means rockets must carry their own oxidizer along with their fuel. Liquid-fueled rockets store their fuel and oxidizer in separate tanks and combine them in the engine. Some common combinations include liquid hydrogen with liquid oxygen or refined kerosene with liquid oxygen. These propellants are pumped into the combustion chamber where they ignite and produce extremely hot gases that are expelled through the nozzle. Liquid propellant systems allow engineers to precisely control how much propellant enters the combustion chamber. This means liquid engines can often be throttled, shut down, and reignited mid-flight. Because of this flexibility, liquid engines are commonly used in upper stages and spacecraft that require precise maneuvering. Solid rocket motors, however, work differently. Instead of separate liquids, the fuel and oxidizer are mixed together into a solid compound. Once ignited, the solid propellant burns continuously until it is exhausted. Solid rockets are simple and powerful, which is why they are often used as boosters during launches, but they cannot easily be throttled or shut down once they start burning, until they have used all of their fuel. Because of their simplicity, solid rockets are extremely reliable and can produce enormous thrust very quickly. This makes them ideal for providing extra power during liftoff. However, the lack of control means they are less suitable for missions that require careful engine management. In both cases, the basic goal is the same: convert stored chemical energy into fast-moving exhaust gases that produce thrust. Number 3. Newton's third law. Rockets work because of Newton's third law of motion. For every action, there is an equal and opposite reaction. When a rocket engine expels exhaust gases out of the nozzle at high speed, those gases push back on the rocket with an equal force in the opposite direction. This is the fundamental reason rockets move. Contrary to what flat earthers may have you believe, the engine does not push against the ground or the air. Instead, it pushes against its own exhaust. That means rockets can operate perfectly well in the vacuum of space. In fact, that's where they operate most effectively. This idea can sometimes seem counterintuitive because we are used to vehicles interacting with their surroundings. Cars push against the road through their tires, and airplanes push against the air using their wings and engines. Rockets are different because they carry their reaction mass with them and eject it to accelerate. Even if a rocket were floating in completely empty space, with nothing around it at all, the rocket would still accelerate when its engine fires. As long as mass is being expelled in one direction, the rocket will accelerate in the opposite direction. So by continuously throwing mass out the back of the vehicle at high speed, the rocket is able to steadily accelerate forward. Number 4. Delta V. Delta V simply means change in velocity, where the change is represented by the Greek letter delta. In rocketry, delta V is treated similarly to how we would treat gas in a car engine, as having more delta V means you can travel further and have longer missions. The only difference is that delta V is not necessarily dependent on the volume of fuel you have, as we'll see shortly. This is because every maneuver a spacecraft performs requires spending some amount of delta V, or simply put, requires changing its speed. Because space missions involve many different maneuvers, engineers treat delta V almost like a currency. Each maneuver requires spending a certain amount of this velocity change budget, and once the spacecraft runs out of delta V, it can no longer significantly change its trajectory. For example, launching into orbit, adjusting in orbit, traveling to another planet, landing on a moon, or returning home all require you to change the velocity of your spacecraft in some way. Mission planners, therefore, calculate delta V budgets for every mission to ensure the spacecraft carries enough propellant to complete its journey. Importantly, delta V does not necessarily represent the rocket's final speed, but rather the total amount of velocity change the vehicle is capable of producing. A spacecraft might accelerate, slow down, and change direction many times during a mission, and each maneuver subtracts from the total delta V available. For example, a spacecraft might first accelerate to leave its starting orbit, then perform another burn to enter the orbit of another planet, and finally perform additional burns to land or return home. Each of these steps consumes some portion of the total delta V budget. Because of this, managing delta V efficiently is one of the most important aspects of spacecraft design and mission planning. Number 5. Tsiolkovsky rocket equation. The rocket equation links a rocket's delta V to its mass and engine efficiency. It shows that rockets must carry enormous amounts of propellant in order to reach high speeds. The equation reveals a simple but powerful truth. The more propellant a rocket carries compared to its empty mass, the more delta V it can achieve. As the rocket burns fuel, it becomes lighter, which allows the remaining propellant to accelerate the vehicle more effectively. This happens because the rocket gradually sheds the mass of the propellant it has already burned. Early in the flight, the rocket must accelerate both the spacecraft and a large amount of fuel. Later in the burn, much of that fuel has already been used, so the remaining propellant is accelerating a lighter vehicle. This is why rockets are often extremely large, even when carrying relatively small payloads. Most of the rocket's mass at launch is not the spacecraft or cargo, but the propellant needed to accelerate it. The rocket equation also explains why reducing weight is so important. Even small reductions in structural mass can significantly increase the total delta V a rocket can achieve. This is why engineers spend enormous effort designing lightweight structures, efficient engines, and carefully optimized vehicles, because every kilogram saved in the structure can translate into additional payload capacity or greater mission capability. Number 6. Rocket staging. Staging is the practice of building rockets in multiple sections that can separate during flight. Each stage contains its own engines and propellant tanks, and once a stage runs out of fuel, it is discarded. Dropping empty stages dramatically reduces the mass of the remaining rocket. Since the rocket equation depends heavily on the structural mass of the rocket, removing dead weight allows the upper stages to accelerate much more efficiently. You can think of staging as shedding unnecessary weight as the rocket climbs higher. Once a stage has finished its job, carrying its empty tanks and engines further would only slow the rocket down. Most orbital launch vehicles use 2 or 3 stages. The first stage provides enormous thrust to lift the rocket off the ground and push it through the dense lower atmosphere. Once its propellant is exhausted, it separates and falls away. The second stage then continues accelerating the payload toward orbit using an engine that is optimized to work in space. Sometimes, additional stages are used for missions that require additional energy, such as sending spacecraft to the moon or other planets. Each stage is optimized for a specific portion of the flight. Without staging, it would be extremely difficult for rockets to reach orbital velocity. A single-stage rocket would need to carry far more propellant and structural mass, making it much less efficient. Number 7. Gravity turn. A gravity turn is a launch maneuver used by rockets shortly after liftoff. Instead of flying straight up, the rocket gradually tilts over and allows gravity to help curve its path toward orbit. This maneuver is important because orbiting a planet requires horizontal velocity, not just altitude. Simply flying straight upward would waste enormous amounts of propellant fighting gravity. At first, rockets do climb almost vertically in order to quickly clear the launch tower and escape the densest part of the atmosphere. However, after a short time, the rocket begins pitching slightly away from vertical. As the rocket accelerates, gravity naturally pulls its trajectory into a smooth curve. This allows the vehicle to build horizontal speed while continuing to climb above the atmosphere. Ideally, the rocket only needs a small steering input early in the flight. After that, gravity itself helps shape the trajectory into the optimal path toward orbit. By letting gravity help shape the trajectory, the rocket minimizes wasted fuel and follows a much more efficient path toward orbit. Number 8. Orbital velocity. Orbital velocity is the speed needed to stay in orbit around a planet. For low Earth orbit, spacecraft must travel at roughly 7.8 kilometers per second. Or for Kerbal, it's around 2.2 kilometers per second. At this speed, the spacecraft is constantly falling towards the center of the planet due to gravity. However, it is also moving horizontally so quickly that the surface of the planet curves away beneath it. As a result, the spacecraft keeps missing the ground and continues falling around the planet indefinitely. This state of continuous freefall is what we call orbit. An orbit can therefore be thought of as a balance between gravity pulling inward and forward motion carrying the spacecraft sideways around the planet. As long as this balance is maintained, the spacecraft will continue circling the planet. Reaching orbit therefore requires far more horizontal speed during a launch than most people might expect. Rockets don't simply fly upward into space. Instead, they must accelerate sideways until they are moving fast enough to circle the planet. Interestingly, the required horizontal speed actually decreases the further away our spacecraft is from the planet, as objects orbit slower as their orbital radius increases. However, it is worth noting that not all orbits are perfect circles, and the majority take the form of an ellipse. It is even possible to get orbits which don't form a closed loop at all, provided the spacecraft's velocity is high enough. Achieving such high speeds is what makes interplanetary travel possible, as it is how real-world spacecraft leave Earth to travel to the Moon, Mars, and beyond. And those are 8 of the most important concepts behind how rockets actually work. If you understand these ideas, you already understand the foundations of modern rocketry. If you enjoyed this video and want to learn more about orbital mechanics, spacecraft design, and the physics behind spaceflight, be sure to check out my other videos and subscribe for more rocketry content.